this program, we'll start by considering the wide range of products that can be sustainably sourced and engineered from the forest, focusing on the vast boreal forests that circle the globe. We'll hear, for example, how the inherent properties of wood can both prevent the spread of pathogens and alleviate the environmental burden of the textile industry. We'll learn how sunlight can be harvested to produce chemical compounds via a process that uses nanocellulose in combination with unicellular algae. We'll explore the potential use of nano-sized lignin particles and how enzymes can be mobilized to produce novel cellulose-derived materials. Finally, we'll examine innovative ways of using biocompatible materials in medical applications, such as internal implants and optical sensors. For decades, pulp and paper research has been focused on resolving the detrimental effect of the hygroscopicity of cellulose.
Obviously, you know what happens when you put paper in water. It's an irreversible change, it never gets back, and of course it's detrimental to that application.
But what if we took the naturally hygroscopic property of lignocellulose and turned it to our advantage? Several research teams from Finland are currently working on this.
I find that angle, that aspect, kind of mind-opening in a way that there is so much you can actually think of really exploiting this high hygroscopicity and the strong water interactions in materials science and materials engineering. We are aiming at revealing the deeper understanding on water interactions and how cellulose and hemicelluloses are binding water, because we know that it is one of those features which really defines these polysaccharide materials. And when we go to the nanoscale, it means that this hygroscopicity is even enhanced, because there's so much more surface area which can bind water, and that's why it's very relevant from very many application points of view to understand the water interactions.
In a project called Probe with Water, Finland's researchers stumbled upon a fundamental discovery.
We wanted to know fundamentally how hemicellulose affects the water interactions with cellulose. So what we do normally when we are researching or investigating water interactions, one of the routes that we take is that we make model films, so tiny films with tiny thickness, just 10, 20, 30 nanometers.
And that requires that we need to dissolve the hemicellulose in this case. The problem is that xylan is quite limited in solubility. And we do have some tricks how to make it soluble, but we also had some challenges when our postdoc Chujun worked with the hemicellulose fraction, and she did quite a lot of efforts finding the temperature and DMSO as a solvent and using time and this combination. It's quite narrow window actually where you have the xylan fraction as a soluble.
And according to the literature, it should be easily dissolved in DMSO, but I noticed that our xylan cannot dissolve in DMSO, so I tried to increase the temperature to increase the solubility. And surprisingly, we found a very interesting nanoparticle were formed during the heating process by the AFM imaging. And this is a starting point when we found the xylan nanocrystal.
And we were quite excited about that because hemicellulose nearly always has been described as an amorphous polymer, so that it does not form crystals. In plants, certainly it does not. If you isolate it from plants, there are some accounts in the literature, a handful really, with maybe fingers of 1 or 2 hands you can count the examples, old articles where they have managed to do some kind of crystals, but never these needle-like nanocrystals.
This type of direct evidence where we could actually control the growth of the crystal as a function of temperature and time in this DMSO system, that type of behavior hasn't been observed before. What is really fascinating in the research work, that you can actually end up in something completely different than first expected.
And what's more, the team soon found out that they could control the size of the crystals, opening a path to novel uses, perhaps even in electronic appliances.
Right now, we are thinking to use our nanocrystal into the liquid crystal field because liquid crystal is like an intermediate phase between a liquid and a crystal. So it has some physical attitude, like physical properties, like a liquid, which means it can move in one direction. But in the meantime, it also has some solid properties. For example, it has sufficient ordered structure to offer them some anisotropic structures. So liquid crystal is a very popular material, like a smart material for like a computer display and a biosensor. So in our case, we are thinking to use our xylene nanocrystal like a liquid crystal because we can control the size of our crystal. So maybe we would find some very interesting, unique properties and applications for the future.
In a Finseris project called Sasamis, physicists Paavo Pentila and Antti Pajanen have been studying at the atomic level the properties of elementary wood fibrils found in plant cell walls.
Exact location of the Hemi Cellulose is not clear because even in spruce, of which we know quite a lot now, even there we know that also all of the components like cellulose, hemicellulose and lignin are somehow linked to each other, so they are close to each other.
The unique aspect of the Sasamis project is to integrate X-ray scattering measurements with atomistic simulations to test hypothetical scattering patterns computed from the atomistic models against the measurements, and in this way to gradually refine the models and to get a clearer picture of how the cell wall nanostructure looks like and how it responds to changing moisture content.
The Sasamis project has generated atomic-scale models of the structure of the cellulose microfibril bundles that predict the location of hemicellulose in natural wood. Combined with experimental data, these may enable us to understand and then manipulate the interactions of wood-derived materials with water.
Wood in general is suitable for the X-ray scattering measurements because it has a very strong orientation of the fibrils.
When the cell wall absorbs moisture, it swells, and the swelling is seen at the level of individual cellulose microfibrils and microfibril bundles. From the scattering data, we see an increase in the interfibril distance, so plain swelling. But what is interesting is the mechanism that leads to the swelling and what happens in the space between the microfibrils that is, according to current knowledge, occupied by hemicelluloses.
I think the role of water is very crucial for the properties of wood as a material on one side, and on the other side also for a lot of applications from wood and basically all kinds of plant cell wall based materials. Because water is everywhere in the nanostructure, and it also is related to how what is the accessibility of the different components in the structure. So this is important, for instance, for fractionation of biomass.
This research also enables us to exploit the hygroscopic properties of cellulose in specific applications, rather than just design ways of getting around them.
Many of the current commercial applications, they are based on these hydrogels, actually. So that it's used as a growth medium, for example, for tissue growth. And these are a genuine product, what is in the market at the moment from nanocellulose. The thing is that it's used, even in those applications, it's used as a passive environment.
The EU-funded FuturaLeaf project goes beyond just using nanocellulose as an inert environment, instead employing it to design a complex matrix for the cultivation of microalgae.
We hope that we can, I would say, revolutionize the solid-state cell factories in a way that we are getting out from these conventional dispersion cultures to solid hydrogel layer or film type of cultures where we can increase the cell density and decrease the water intensity of the system, and also to make these cells live longer, improve the cell fitness and improve their productivity.
Such cell factories represent a crucial platform to produce industrial chemicals to replace those derived from petroleum.
One of the molecules is ethylene or ethene, which is the basic starting material or starting molecule for polyethylene, the most common plastic, for example. And plants do produce ethylene in very trace amounts, mainly for signaling purposes. And they can actually create these kind of strains of cells where it's really emphasized and blown up the production of ethylene.
Traditional methods for growing microalgae have intrinsic limitations.
If you traditionally cultivate the cells within this suspension, so basically in liquid aqueous conditions, it means that the huge potential that these cells have is only held to a small fraction, because you have uneven distribution of light, you use huge amounts of water and energy, and also you are creating the environment for the cells that they actually not metabolically. They do not want to produce the chemicals. If you think about it, you put them into dilute suspension, they want to grow more to fill that void in the suspension.
The nanocellulose matrix thus offers unique improvements in algal cell culture.
Well, because we have the cells in the matrix, the light comes directly to the cells that are stationary. So in a normal culture, you would have the cells kind of mixing around, and some are illuminated and some are in a dark periodically. But with this approach, we can get the cells to be constantly illuminated in a way that supports their metabolism.
They are shielded from the environment, and also because now they are tightly bound within this gel-like structure, it means that the metabolic activity of the cells is actually not geared towards creating more biomass anymore, because there's no space. And that means that all the energy that comes from sunlight, or more of that energy, is then targeted towards the chemicals production.
The engineering of the actual cells is being carried out at the University of Turku by Jogurt Alverdieva-Rinne and her team.
Our aim in this project that to use photosynthetic cells not as a biomass for biorefineries, but as biocatalysts which can convert solar energy and CO2 into the targeted molecules. And here we need also synthetic biology tools, because cells don't produce all the compounds we are interested. We can use emerging synthetic biology technology to bring foreign production pathways to the cells and force them to produce the compounds, chemicals we are interested.
Meanwhile, the materials scientists at VTT are aiming to create a highly engineered architecture for the nanocellulose matrix, inspired by nature, so as to optimize cell productivity.
Yeah, so if we think about the green leaf, it has layers. It has a very, very dense layer at the top, which allows light penetration, allows gas exchange, keeps out moisture or keeps in moisture. And then when you go down, you have something that's really porous, and again, exchange of gases, nutrients within the material. So we do have to think about those things when we plan this architecture.
One of the research challenges is to stabilize the nanocellulose matrix.
We're working with tempo oxidized cellulose nanofibers as the matrix material, and even though it has some very good benefits in terms of the immobilization application, such as transparency, which is, of course, as we want the light to be distributed evenly, it is a good thing. But tempo CNF is not stable in water as itself, so we need some kind of strategy to improve the water stability, because we all, of course, need it to be stable and endure in aqueous conditions. So I'm investigating a Hemi Cellulose, which could act as a cross-linking agent to improve the water stability and the mechanical properties of the Tempo oxidized cellulose nanofibers.
In another water-related application, nanocellulose is being harnessed to address one of the most daunting threats to the environment, nanoscale microplastic pollution, which is increasing exponentially. Each cubic meter of water on our planet contains, on average, over 8 million microplastic particles, and that's only the particles that we can currently detect. A Finseries research team is addressing this invisible threat using nanocellulose membranes.
With our materials and with our approach, we can even collect the smallest fraction of these nano-sized colloidal particles.
Nanocellulose is highly hygroscopic, so we utilize the high hygroscopicity in conveying the plastic particles inside the structure, and once inside the structure, they actually stay in the porous network.
This groundbreaking research has already attracted international media attention. Apart from its potential use in water filtration systems, such as in washing machines, the detection method itself is of great importance.
In general, if you think about different size particles, there are certain methods that suit different size ranges. And for nanoparticle detection, most of the methods available are really in-lab clean systems where you would be characterizing your produced nanoparticles, for example. And this creates a gap in methodology that allows detection of really small particles from environmental samples or samples that are not, let's say, uniform or ideal.
We have used these surface-sensitive methods such as quartz crystal microbalance to detect the capturing of even the smallest nanoparticles. We insert this microplastic solution into the QCMD, and then it works kind of as this small microbalance, so it can detect the mass of the particles once they adsorb on the nanocellulose surface. And it is measured with frequency, so when there's a decrease in the frequency values, we can say that actually the nanoplastic particles are adsorbing on the surface. And then by SEM imaging, scanning electron microscopy, we have imaged the films, and we can actually see even the nano-sized particles in the nanocellulose mesh.
Microorganisms and lignocellulose come together on many different levels, and the global pandemic has highlighted the importance of this work.
A lot of the personal protective equipment, or PPE, is being made out of petroleum products. So surgical masks, N95 masks, are made predominantly from polyethylene, polypropylene. Very nice chemicals, they're very chemically resistant, but that also makes them not biodegradable. Although they're only used on your body for minutes to hours, they will, when put on the ground, last hundreds, if not thousands of years. So we have some interesting opportunities to take bioproducts, use them in the medical industry, not just inside the body, but also outside the body, to solve these problems, to help us create materials that are more environmentally friendly.
Bio-based alternatives could offer not only a more sustainable path to solve these issues, but also ways to cope with microbes more selectively.
So actually the problem with many of the current solutions is that they are generally toxic. They kill all the bacteria. And the worst case scenario is that they don't kill all the bacteria, they kill all the good ones, because the good ones are usually easier to kill than the real toxic ones. So then these toxic ones have freedom to grow. So this is like the worst case scenario of using these general methods.
Plants have evolved over millions of years to resist assaults by bacteria, fungi and viruses. Some key antimicrobials are even incorporated into the structural carbohydrates of plants. At Aalto University, Monica Österberg's group has been studying the properties of lignin and cellulose nanoparticles in combating the spread of pathogens.
Well, what we have recently done in Finseres is that we have a project where we combine nanocellulose with nanolignin. So the nanocellulose is this HEF-cell cellulose, so it's enzymatically made and it can be produced in quite high consistency. And then we combine this with these spherical colloidal lignin particles. And in the lignin again, that gives this antimicrobial properties. So what we are researching is that we are looking into making different kind of coatings that could be used on textiles or on tables as a cheap and also a natural antimicrobial coating.
Our main focus have now been in this bacteria that causes hospital infections, this MRSA, and we have found out that some of Monica's products are able to kill those, but are not necessarily harmful for other microbes, because, well, the world is full of microbes that are not harmful at all, and those we don't want to kill.
Later in this program, we'll talk more about these two new materials, colloidal lignin particles and HEF-cell nanocellulose. They have an important property in common, low production costs, which separates them from more conventional nanomaterials. But for now, let's return to the antipathogenic properties of wood. Plants also have various classes of secondary metabolite, for example polyphenolic compounds, that perform many functions, including the killing of pathogens.
Because the trees need these compounds also for their own defense, so they need to fight against different pathogens, fungi, and other organisms attacking the trees. And usually these compounds are located in the bark of the tree, so it's kind of a shield against these nasty pathogens.
Although it has potential as a side stream of the forest industry, the bark is currently not put to good use.
At the moment, most of the bark is still used for energy production in the industry, so we could use it in different cascade processes to first obtain these active compounds and then use also the rest of the biomass for different purposes before it's finally burned for energy.
In a large, recently established research collaboration at Luke, the Natural Resource Centre of Finland, these compounds are now being developed for commercial use.
Yes, we have at the moment the project funded by Business Finland. It's this Corona Co-Creation Fund, and we are collaborating with University of Jyväskylä. We have Professor Varpu Marjomäki's group in cooperation, and they are virus researchers. And together with them, we have found already very promising results of different tree extracts. And the extracts have been tested and shown activity against different virus types, including enteroviruses, which are really nasty ones to kill, also with ethanol-based disinfectants. And then we have found activity against the seasonal coronavirus and also the virus which is causing this current COVID pandemics.
The research aims at fast-tracking commercial products. In a recent publication, the team at Luke has mapped the entire process of creating extra value from bark.
We have studied this kind of cascade processing, where the idea is that we first, for example, extract valuable polyphenols and other water-soluble extracts out of the side stream. It can be, for example, bark, and then they are utilized for high added value products. And then the remaining biomass can be still used for other processes. So we are kind of combining different unit processes together in order to get most out of the raw material. And after the extraction process, the residues have been, for example, taken to the slow pyrolysis process. And from that process, we can get out of tar and we can get biochar. And then pyrolysis liquids. And those liquids are kind of a residue which can again be directed to biogas process, AD process, and from that we can get out of biogas, for example. And the solid residues can also be directed to this AD process. By this way we can get really most out of the raw material.
In fact, similar findings have already been applied commercially. Nordshield, a Finnish startup founded in 2016, is entering the market with wood-based antimicrobial coatings.
So we use these components from the side streams of the pulping industry and make it into the Nordshield technology, which is present at different types of product families. One product family is a water-based product that can be used for example, textile treatments. And there the Nordshield technology will form an ultra-thin layer on the fiber surfaces. And this will be like a physical shield and will reduce the microbes on the fiber surface. On the textile side, we are working both to fight against fungi, so mold during transportation. For this we have a certain technology in combination also with a small amount of biocide to take care of that. Then we also have a product that we call BioLayer, which is an antimicrobial and antiviral technology which can be applied onto textiles. So it will reduce not only bacteria on the textile but also viruses. Our technology also inactivates enveloped viruses, to which, among others, also the coronavirus belong.
Wood is a highly versatile material. So far, we've only looked at how it can fight pathogens, but next we will look at how the inert qualities and non-toxicity of wood-based materials can support medical applications.
For a lot of implantable materials, you want them to be biocompatible. You want them to be able to be not rejected by the body.
This is no small issue. Implant-related infections can lead to serious complications for patients, and in some cases even death. Lignocellulose-based materials are surprisingly biocompatible and could therefore potentially benefit millions of people.
And a lot of the carbohydrates that are readily available in the forest allow us to introduce very interesting biocompatibility into our implantable materials. We can take that cellulose, we can implant it in the body. It's not rejected by the body nearly as much as a lot of the other polymers that are potentially used.
At Aalto University, the Biodesign Project is addressing how to turn these properties of cellulose-based materials into useful applications.
Biodesign Project, in a nutshell, is basically a project where we are put into a real-life hospital environment to look for real-life needs. And then after that, when we found the need, we start to think about how we could actually solve the problem.
One of these real-life needs is replacing the plastic mesh that is often used during surgery to correct organ prolapse.
We figured out that this is a big problem. 1 in 5 women suffer from pelvic organ prolapse during their lifetime. And out of this large number, 11% of females, they would require surgeries for treating this problem. And also, out of this number, 30 to 40%, they need meshes during their surgeries. And since the aging population is increasing, this number is going to increase over time.
But what is the problem with the current meshes made from fossil-based materials?
Yes, actually in 2016, plastic meshes were reclassified from Class 2 to Class 3 FDA products. And also in 2019, the transvaginal mesh were totally banned from the market due to all different problems that they caused in the patient, including bleeding, urinary problems, inflammation, and actually most of the patients were reporting so many negative effects that these plastic products were banned, and big companies, they have to withdraw their products from the market.
With biologically derived materials, these problems can be overcome. Wood, of course, breaks down in the natural environment due to the enzymes that degrade cellulose and similar polymers. But these enzymes are produced by fungi, bacteria, and a few insects, not by humans. so bio-based meshes are long-lived as well as non-toxic. In another large collaborative project, methyl cellulose-based optical fibers are being studied for possible use in biomedical sensors.
They probably can't replace the classic optical fibers, which have a very small attenuation, and you can transmit the signal for tens of kilometers. But there are lots of small-scale applications, for example, in a car, in automotive industry in general, and also in biotechnical applications to mediate or sensing information from the tissues to outside world. So there one doesn't need to have tens of kilometers signal transmittance, but perhaps this length, for example, to convey, for example, signals from the tissue beneath the skin to some sensors.
They are also being used for biomedical application such as localized laser surgery. So that means you don't have to introduce some special surgical device. Instead, you just shine with a laser in a localized where you have a specific disease, for example, cancer or tumor. But one of the biggest problem in the glass optical fiber is that they are brittle, and they're brittle at the same time they will damage the cells.
Cellulose-derived optical fibers do have certain advantages over those made of glass, for instance.
One benefit of cellulose is that it's very easy to chemical modify, so we can make totally new type optical materials that are not possible to do with synthetic materials.
We can spin these fibers at room temperature, and we can spin the fiber from 4 degree up to 37 degree. And that is the limit for many of the biological molecules if you want to incorporate inside the fiber, if you are looking for more advanced therapeutic applications, which is not possible in polymer optical fibers, just because you have to spin at 180 degrees Celsius, 200 degrees Celsius.
We can make very flexible and soft fibers out of it. It is actually really tough. You can stretch it, it doesn't break. You can also bend and twist it. It doesn't break either.
At the same time, it has a very good refractive index that is very close to the polymer optical fibers. And if you can tune it just by changing the chemical groups or functional group. It has very limited scattering, so that is rather unique.
Utilization of bioproducts for implantable materials offers a huge range of different opportunities. We can interface, for example, optical fibers into the brain, transparent electrodes using bioproducts as carriers to replace traditional metals. We can use these to harvest energy from the body, piezoelectrics that will either move or gather energy from just our body movements. All of these things are built on structures of bioproducts that we can utilize in a variety of different types of ways.
Kraft pulping remains the primary method for fractionating wood, and should be so for years to come. However, novel processes enable us to isolate lignocellulosic building blocks with better or entirely new properties. Such methods increase the yield of higher value fractions, as well as creating new functional materials.
The conventional forest sector is fundamentally the deconstruction of forest biomass into materials like lumber, plywood, OSB, paper products. The future bioeconomy is fundamentally the molecular deconstruction of the base polymers and the nanofibers that are found naturally occurring in the forest biomass, and using technology to create high-value materials, high-performance materials, as well as high-value chemicals and fuels. This biorefinery framework is really aimed at extracting the maximum value from our precious forest resource.
About future biorefineries, so I would say so that we have already great achievements here. Great job is done here in Finland by all these big giants. But what if we could try to go even a little bit beyond that one. Even if we are a little bit more brave there and have courage to do it.
Kraft pulp serves as a good starting material for numerous high-value derivatives. A startup called Nordic BioProducts is commercializing one of them, the Aalto cell patented microcrystalline cellulose.
The other existing methodologies are using actually not kraft pulp, but dissolving pulp. But this Aalto cell is the only patented technology that can utilize kraft pulp, which we have much more here available in Finland. And so we're taking kraft pulp and then we hydrolyze it into smaller pieces. Basically, we're just making a micrometer size particles of pure cellulose. And these particles we can then further process so that they are applicable in several different possibilities, if I would say, applications, like textiles, like plastics, and so on, so on, so on.
Hemi Cellulose is currently an underused renewable resource. It is the second most abundant component of forest biomass, yet nearly all of it is just burned in the mill nowadays.
So one of the big challenges with recovering hemicellulose is that individually researchers with individual biomass types have found good strategies, but there's no unifying theory or approach or way to predict outcomes. So anytime we want to change something, we sort of have to start all over, which is not very efficient. But the good news is that because so many people have tried all these individual approaches, we have a lot of data available to us in the literature. However, making sense of all that data is a little bit beyond our human perception, and so we can take advantage of emerging machine learning opportunities. So I've created a collaboration with Dr. Yenkai Kao here at UBC, and I bring the hemicellulose expertise, he brings the machine learning expertise, and now we're taking advantage of statistics, mathematics, and computer science to examine all of this hemicellulose data to look for patterns and build new models that can help us spot new approaches, new efficiencies, and new strategies to try.
Heather Trujano from UBC has worked on putting it to much better use.
So hemicellulose has a lot of opportunities for application. So one application is to make it into films that could be really great food packaging. Another application would be to produce hydrogels that could be used for timed drug delivery, for example. And then hemicellulose is made of sugars, and those sugars could be transformed into low-calorie sweeteners such as xylitol.
Xylitol is an interesting product because it can be used in chewing gum, candies, food, and in pharmaceutical applications. It can also, or could also, be used as a renewable component in polymers, in material applications. And today it's produced chemically at high temperatures with toxic catalysts.
In fact, at VTT, Merja Pentilä's group has successfully turned hemicellulose C5 slurry into xylitol using modified yeast strains.
We have engineered a special yeast species to use the C5 waste fraction from an organosol process and to produce xylitol. Not only did we make industrially relevant xylitol yields, but we also engineered the yeast strain so that it can remove the acids from the slurry that would otherwise be harmful for the yeast strain.
In our earlier example of implants, the benefit of biologically sourced materials was their non-biodegradability inside the human body. Our next harnesses the very opposite process, the breakdown of wood by fungal enzymes.
So historically, people have looked at this interaction between trees and their microbial counterparts from the perspective of finding new enzymes, new biocatalysts that are able to break down woody material. And that's had a long history of success, for example, in developing new biofuels and in the biofuels industry. One of the things we're really looking forward to in the future is to find enzymes, find biocatalysts that allow us to add new functionality into materials. So rather than taking a tree and breaking it down to its component sugars, we might want to stop partway and harness those materials and reconfigure them to make new materials, or we can take those biochemicals that come out of trees and the forest resource and use other enzymes to add new chemistry to them.
Enzymes are, of course, fundamental in biology. Their catalytic activity and selectivity determine the chemistry of all living systems.
We know that currently there are more than 5,000 different types of enzyme activities, so they are very versatile and they are catalyzing very versatile reactions. In the nature, enzymes participate, for instance, degradation of biomass, and they are very important in the carbon recycling.
Without the degradative enzymes secreted by fungi, dead trees would remain intact for tens of thousands of years.
The natural or wild type enzymes as such are very seldom suitable for industrial purposes. Therefore, we need to have means to modify the enzymes. On the other hand, we need to also have good methods to produce the enzymes. And during the last and recent years, we have had a lot of development in that area. We have been able to produce enzymes in a more cost-efficient way, in a higher amounts, and also with enzymes with better and improved performance.
Apart from the traditional hydrolytic enzymes, another group of enzymes has attracted increasing interest.
I think very interesting discovery was made some years back in Norway by Professor Vincent Eising. So he discovered that in addition to the hydrolytic enzymes, there is also a very important oxidative activity.
This activity has been studied in a large EU-funded research collaboration involving groups in Norway, Finland and Austria.
So this enzyme activity is able to make oxidation in the crystalline part of cellulose. So it oxidizes either the C1 or the C4 carbon in the glucose ring. So this oxidation generates oxidative groups. And more importantly, I think it loosens the crystalline structure. So the crystallinity will be lower, and this means that this type of material treated with this enzyme would be more accessible for chemicals, for instance.
The process has already been successfully explored in the conversion of lignocellulose biomass into biofuels, in the production of cellulose nanomaterials, and for improving the solubility of cellulose for making regenerated textile fibers. In another large research endeavour at VTT, enzymes have been harnessed to create nanofibrillated cellulose, or NFC. Normally, NFC is made with a high-pressure homogenizer at a pressure of up to 1400 bars. The enzymatic HEF cell process obviates the need for this huge energy input.
We have studied cellulases for fiber modification over 20 years. And in those studies, we have seen that this particular cellulase can fibrillate fibers.
Cellulases are produced by organisms that are widespread in the environment.
HEF cell is a new type of material. It's done with the combined action of enzymes and a gentle mixing.
The process has several advantages over traditional methods.
The first thing is that the process is very simple, uses much less energy as the traditional process. And finally, the end product is in high solids content, which means that it's not anymore a hydrogel. It's more like a paste.
The properties of the material are completely different. And these properties enable the use of the nanocellulose material in different applications that would not be possible with traditional grades.
Stina Grönqvist and Jaakko Pere from VTT believe that the novel material opens up completely new possibilities for the biomaterials industry.
You can upscale it quite easily. There is already equipment available in an industrial scale that could be used, and the enzyme that we use is a commercial enzyme product. Traditional nanocelluloses are used in different types of packaging materials, like films, but it could also be used in coatings. And to be honest, at the moment, we don't even know all the possibilities for nanocellulose.
One of the more surprising applications for this new material is as a flame retardant.
We noticed that when you mix Hemi with pigments, you can make coatings which has flame retardant properties. And that's totally new type of way to think about flame retardants, because nowadays all those solutions are more or less chemicals.
Most surfaces, such as textiles, plastics, electronics and furniture, are treated with flame retardants, usually based on bromine. But brominated compounds are increasingly being banned in the EU due to their toxicity. For example, they can cause male sterility. Another affordable way of producing nanomaterials has been developed at Aalto University through Monica Österberg's work on colloidal lignin particles. Lignin, despite its potential, has challenged researchers and engineers for decades. Specifically, how to get higher value products from this complex fraction.
Lignin chemists have been arguing about the exact lignin structure, so someone might say that it's actually not three-dimensional, it's like linear in the nature, but when you extract it from the pulping, then it reacts with it within the lignin and with the other lignin molecules and makes this three-dimensional structure. So actually this argument has been going on in the lignin community for a very long time. So I think that if you can't even agree on the structure, that might be one reason why it's difficult to utilize.
But Monica has found a way to overcome this problem.
I read a paper where they had used acetylated lignin and they could make this spherical particles. Since I had been working with nanocellulose for a long time, that this could be very nice to see if we can use these well-defined lignin particles. And then our first breakthrough was to show that we could make these spherical particles without any modification of the lignin. So using this kraft lignin that is the one that is most available. So it's a cheap raw material, and then we can just dissolve it in an organic solvent, and then when we put it into an anti-solvent, the water, they spontaneously self-assemble into the spherical particles.
Self-assembly thus creates perfectly shaped, nano-sized lignin particles.
They are all perfect spheres because that's nature. That's how nature wants it. It's the lowest energy form. If we don't tweak the method, we have a bit of variation in the size. By changing the solvent we use, we can make smaller or larger particles. So we can already quite well tune the size of the particles that we are getting.
Nanomaterials are usually very expensive to produce. However, these nanospheres are surprisingly cheap and easy to make.
The process is very cheap. So when we have calculated on the cost of the process, I think we are below €1 per kilo. So, and that's a lot of the cost comes from the lignin. So the process is actually just dissolving lignin and then precipitating it in water.
These nanospheres can be applied commercially in diverse ways.
It makes it much better to use in adhesives and composites, these kind of large-scale applications. But it also opens up totally new application areas that lignin haven't been used. Drug delivery. Well, we have also seen that it works very well as a dispersant and then emulsion stabilizer. Those are also potential ones. And then you can make coatings with a bit of chemical modification. You can make very good coatings for wood or for textiles.
Moving on from nanoscale phenomena and how the components of wood interact with the environment, we'll now turn to applied R&D on novel high-volume products. This is essential if we are to replace fossil-based raw materials. The fastest growing area for new cellulose applications is textiles.
One of the
great needs globally of the textile industry is to find alternatives for cotton. Growing cotton and transforming it into textiles uses immense amounts of water, which is ecologically unsustainable. And for this, we want to find an alternative from cellulose, from the wood industry.
Well, the demand for textile fibers in general has been growing immensely during the past 50 years. And today we are producing over 100 million tons of textile fibers globally. Most of the textile fibers today are produced from oil, over half. The second largest raw material is cotton, and then about 6% is based on wood. So this is a starting point. Oil-based textile fibers are still growing.
Polyester definitely is a problem, oil-based and microplastic forming material.
But what to do with the demand for cotton-like fibers? This is the window for the forest-based and wood-based fibers.
There is an increasing need for cellulosic fibers, no doubt. And also that for the raw material base there is need to combine the recycling for the same. So it's not either or, but it's both. Because we need to have in a rough 10 years time something like 50-60 million tons more textile fibers. So it's a kind of consumption explosion. And so everything is, so it's an ocean of possibilities at the moment, more than threats.
Let's now consider some new technologies under development in Finland that can meet the growing need for sustainable textile fibers. Ways to generate spinnable fibers from pulp, such as the viscose method, have been with us for a century or more, but they are highly polluting, so a replacement is urgently needed. Medster Fiber opened their pilot-scale facility in Äänekoski in 2020. The first of its kind, it uses ionic liquids to dissolve pulp, from which cellulose fibers can be regenerated. Upscaling to a pilot plant was obviously a bold step, given that the process itself is still under development in the lab setting.
The development world has changed significantly during the past 20-30 years. It used to be very linear. You made your basic science, and after that phase you went into applied science, and after that phase you went into the industrial research and development. But today this all happens in parallel, so you have to be engaged in all of these levels at the same time. And when you go into your industrial research and development phase, you don't have all the answers, even the basic answers, some are open. So you have to just take higher risk, and this is all due to the globalization and the speed of things happening.
The ionic liquids developed by Ilkka Kilpeläinen's team at the University of Helsinki are the key to the ion cell process, pioneered by Herbert Sixter at Aalto University, and now reaching pilot implementation stage.
What is new and also different to other pilot plants in the same field is that we run in a closed loop operation already at this scale. The capacity is 1.5 kilograms per hour of fibers. We have 2 lines. We have on each line 5 spinnerets. At the moment we have close to 1 kilogram per hour capacity on each spinning line.
The ion cell team is now focused on solving some of the remaining challenges with the wood-based fiber.
The high-tenacity cellulose-based textile fiber compromises the elongation, and on the other hand, that is also vice versa. So to compete with synthetic textile fibers, we have to improve the mechanical properties of cellulose-based textile fiber, meaning we have to increase this tenacity and elongation simultaneously to have high toughness cellulose-based textile fiber.
In recent publications, Kanis has reported how superior tenacity and elongation properties of the ion cell fiber can be achieved by modifying the shape of the spinneret.
Basically, we have done the spinneret geometry change. So we found that if we have longer spinneret capillary, then fiber has, basically cellulose solution has more time to have the alignment of the cellulose molecules. And then at the end, when we have the fibers coagulated, then the cellulose fiber has higher orientation, which results simultaneous increase in tenacity and the elongation. So we also changed the pulp, and which is the high molecular weight pulp with very less impurities. So that also contributed to the high toughness of the ion cell fiber.
Another high priority in the ion cell process is to recycle the ionic liquids.
Basically, these solvents are like any other organic solvent. They can have some degradation because of heat, because of presence of other compounds like water. They can have some reactions with these compounds.
The research has generated a steady improvement in solvent recycling, currently reaching 97% recovery.
And we are, of course, aiming to even increase this amount in the future to surpass 99%. And this is something that I have done in one of my papers, that we have recycled this solvent for 5 cycles. So we recycle, and then we dissolve cellulose successfully, we spin, and then we recycle again, and so on, so 5 times. And we could clearly show that the solvent has been changed in a very minor manner. And the cellulose that we have produced, or the regenerated cellulose, it has had good mechanical properties. And so we could even proceed with Marimekko and produce a dress out of these produced fibers.
The ion cell technology has also been applied in the manufacture of many other end products.
I joined Herbert's group already at the very beginning when he built up this ion cell project. I was then a postdoc, and I was responsible for installing all the equipment to get everything going. And we had a clear focus of converting wood pulp into high-quality textile fibers. And it took all quite long until everything was running, but once it was working, then everything happened really fast. And rather soon we realized that these fibers are not only suitable for the textile applications, which we had in mind in the first place, but could also serve technical purposes. And so then we started to look at carbon fibers. Carbonize our originally textile fibers, our cellulose-based fibers, and we found that we get actually quite high-quality carbon fibers. And more than that, this technology, the ion cell technology, allowed to also incorporate other biopolymers, polymers like lignin, who boosted the carbon content. So we could improve the carbon fibers not only from the technical point of view, but also from the economical point of view. So we increased the carbon yield.
What is the difference between traditional carbon fiber and this new biologically sourced option?
Today's carbon fibers are made from polyacrylonitrile, so PAN, that is an extremely nice material and an amazing precursor for carbon fibers. And with this precursor material, you will get the best carbon fibers that are needed in airplanes, where you really want to have the best quality because your safety is at risk there. When we have to be honest with our bio-based carbon fibers, at least in my opinion, we will never be able to reach this extremely high quality. But that is not needed for bulk applications. So for applications like in a car, for instance, to replace certain metallic parts in car with lightweight carbon fiber composites, carbon fibers made from biomaterial would fulfill these requirements and could offer a solution there.
I met Ali Harlin back in 2014 for the pilot episode of Suomen Tulevaisuus, and the field has moved on substantially since then.
5 years has been like a, space shuttle. So a lot of things has happened, and when we were speaking that time of new inventions in laboratory, now we are speaking about the things which are coming in a piloting, or they are even further. So there is capsule collection coming out. There is even certain material has come to the marketplace first time. And that's really fascinating. I believe quite a lot 5 years ago, but this has been even more rapid than I ever thought it could be.
The Infinited Fiber company is using cellulose carbamate technology. They too have come a long way from the lab. Focusing on using waste as raw material to make textile fibers, they have already partnered with some major global brands such as H&M and Patagonia.
In the recycled textile, where the Infinited Fiber is definitely in, just this week a sub-brand of H&M has sold the first jeans to the open market. So that material is now commercial.
Repurposing waste is a crucial element in the EU's circular economy strategy. An increasingly important trend in the textile industry is to address the sustainability of the entire value chain.
Sustainability of fibers is not only rising from the raw material. So the fiber as such is just 1/3 of the sustainability of the textile life cycle or less. So the next one, which is about the same size, is the coloring and finishing and chemical converting of the fibers when they are already textile fibers.
Textile dyes create 1/5 of all water pollution on our planet. Making sure we use less dyes and that the dyes stick permanently to the fibers rather than leaching out during every wash cycle is a fundamental task for research and industry. In a recently launched EU project called GREET, cellulose fibers are being modified so as to optimize their solubility in ionic liquids and at the same time improve their dyeability.
In the GREET project, we use enzymatic modification and chemical modification in order to improve the properties of the final regenerated fiber product.
So it's not only about replacing the existing fibers or raw materials which are on the market. GREET will offer a production technology which consumes less energy and will consume less water.
With enzymes, we are capable of modifying the pulp properties so that it's more easily dissolved and form good quality dope that can be easily made into a regenerated fiber.
The functionalization used in the GREET fibers opens up new possibilities in the post-treatments of the fibers.
In GREET project, we aim to use paper-grade pulp, which requires much less processing and is more abundant, more available on the markets.
One advantage of using biologically sourced materials is the abundance of reactive hydroxyl groups, imparting versatility to the end product. Another advantage is the porosity of the fiber, compared to synthetic polyesters, for example. Enzymes can gently loosen the polymeric structure, enabling colorants to bind more easily. The BioCellSol technology again uses enzymes to improve the solubility of the pulp.
And this enzymatic treatment improves its ability to dissolve in alkaline solutions.
A company called Spinnova has an entirely different approach to making cellulose-based textile fibers. Their method converts pulp directly to fiber using 99% less water than cotton production.
The process is the core of our technology because we don't dissolve the materials, we only grind them mechanically. We, in a way, open the structure of the cellulosic fiber so that the surface area of the fibers increases. And then a lot of hydrogen bonding can be formed in the drying of the materials.
Established in 2015, Spinnova already employs nearly 50 people.
Today, we are working in our second generation pilot facility in Jyväskylä. We can produce some tens of thousands of kilograms fibers annually, and we aim to scale up the production to first industrial scale mill by the end of 2022.
Spinnova is also commercializing their fiber in partnership with major consumer brands.
some of our cooperations are already public and some are still confidential. At the moment, we are working together with about 10 brands, and we have published a cooperation with the Norwegian Vergans, a sportswear brand, and Finnish Marimekko, a fashion brand, classic fashion brand from Finland, and also with the Danish bestseller that covers several brands.
Woody biomass offers tremendous opportunities to replace fossil-based raw materials. But in order to do this, the emphasis on truly sustainable forestry takes centre stage. Here in Finland, the forest played a key role in bringing the country out of poverty. Today, 80% of Finland is covered in forest, making it one of the most forested countries in the world.
"200 years ago, this was not the case. Finland was one of the poorest countries in Europe, and our forests were overexploited, almost raped, by slash and burn agriculture and poorly done forest management."
Indeed, the Finnish word for rape, raiskaus, was originally applied to the destruction of forests. There was a time when large areas of the country were left barren by such activity. But by the mid-1800s, changes were afoot. Due to the booming growth of sawmills and the paper industry, the forests acquired significant economic value. As the tens of thousands of smallholder farmers began to realize the potential value of the forests on their land, a culture of sustainable forest management developed. The simple rule of planting new trees to replace those harvested became the norm.
A bit over 100 years, our forests has been managed intensively. A lot of R&D, well-organized forest professionals, and hundreds of thousands of private forest owners have created together this remarkable renewable resource, offering all kinds of ecosystem services for all of us. This tree is not growing now. It will wait few months more, and then it will start to grow together with 30 billion other trees in Finland. Together they will produce 1 million cubic meters of new biomass every day. And at the end of the growing season, we will have 110 million cubic meters of new wood in our forests. We harvest every year only 60% of our annual growth. That means that our forest resources increase with about 20 million cubic meters every year. And that 60% of harvest is crucial for this country. It offered last year 66,000 jobs, 4% of our GNP, and 19% of our exports.
People see it as something, if I plant a tree, my grandchildren are going to be the one that actually reap the benefits. But it's seen as a sort of a way of sort of providing for people, and that also gives the motivation to keep it in as good shape as possible.
The carbon sink discussion is also a hot topic. Why are there so many different ways of calculating carbon sequestration?
Forests are a combination of these trees, other plants, and a soil. It is easy to calculate carbon in trees and plants, but it's really challenging to calculate the carbon in soil and especially understand the interaction between the soil and trees and other plants. These models have a lot of uncertainty, especially when we estimate the carbon throughout the decades of forest rotation. However, these models are improving all the time, and we are getting closer and closer to the real amount of carbon in forest ecosystem. In European Union, we have agreed rules how to calculate carbon balance of forests, emissions and carbon sinks. But again, pretty soon those rules are changing again. And that is causing a lot of challenges for communicating about forest carbon issues. Finnish forests are a remarkable carbon sink. The annual net sink is about 30 million CO2 equivalent tons. It is about 50% of all CO2 emissions in Finland. But that is not the case in all countries. Because of forest management and especially because of forest fires, forests can be a remarkable source of CO2 instead of being effective sink.
In Finland, the carbon sink numbers for forest biomass are calculated through one of the world's most advanced biomass inventory systems.
Forest data is really important when running sustainable forestry. Finnish National Forest Inventory is 100 years old. During that time, we have been able to get huge amount of exact data from our forests, and that has been helping us so that we are utilizing the opportunities of forests but not over-exploiting our resources. Satellite imagery we have been using already for decades. Nowadays we are using also LiDAR, photogrammetry and all kind of sensors to get more reliable information and data about forests.
BC has one of the largest forests in the world, and as a result, UBC has developed expertise across the entire forest sector value chain. But I think one of the real opportunities we have is to leverage the science excellence we have in genomics, biocatalysis, and catalysis that are really at the heart, the key technologies used in the bioeconomy. This is deep science. If you look at the Nobel Prizes since 2000, 4 of them have been in catalysis, and last year was biocatalysis. This makes this area of scientific endeavor, research, and innovation one of the very few that combines deep science along with climate action that we can do today, as well as economic development and real jobs in rural communities.
One of the big attractions of the bioeconomy internationally is the biomass is much more democratically distributed than oil. So the idea is to work with those regions that are relatively poor in terms of resources other than biomass, and how can you enhance the quality of life and also look at a new sector, a new industry that's based on this biomass material.
While well-managed forests are a prerequisite for any large-scale use of biomass, the next step is equally crucial: using this precious raw material sustainably, which means maximizing the efficiency of its processing and the value and durability of what's produced.
Sustainable is something that can actually, it's not depleted over time. That's basically what it is. So we'll be able to maintain or even increase that supply. So rather than making things poorer, we should be actually be able to replenish. And I think from my sort of perspective, that is the definition of sustainable. So we can pass it on to the next generation that just keeps on giving and giving more than it gave before. I think what we need to do really is to start thinking more about the sort of the biomass as a sort of a not an abundant resource, but a limited resource. And what does it actually mean then? We have the targets of reducing fossil carbon in our materials. So what we need to start doing is that what is the most effective way of doing that? And then we are basically looking at 2 things. First of all, we need to start thinking about the tree as a tree. So making sure that we use every part of it as much as we can in order to maximize the amount of biogenic carbon that one can use to sort of reduce the fossil carbon in products. The second thing is looking at the circularity. So how can we make sure that the carbon stays in the products longer? Of course, there are a lot of products which are sort of disposable and that's it. But there are also a lot of opportunities for sort of introducing also circular economy more into the bioeconomy. And then, of course, when the aim is to reduce the amount of fossil carbon, then we also have to start thinking that whenever we still need to replenish the carbon from somewhere. So where do we take the virgin carbon? Do we take it from the renewable sources or do we take it from the fossil sources?
Our interconnected future relies on the ingenuity and dedication of scientists all over the globe. And above all, not just in international collaborations like the Boreal Alliance, but by basic scientists and engineers working together, biotechnologists, structural enzymologists, physicists, process engineers, and many others. Science can transform the most basic of materials like wood into thousands of sustainable products, if we take the trouble to learn from nature and from each other. Finserres and its Canadian partners represent such an endeavour, working together towards redefining the bioeconomy for future generations.